Example 4. A couple obtains a loan of $100,000 at a rate of 9% compounded monthly. They decide on a term of 9 years and they make monthly payments accordingly for a 1-year period. At the end of the 1 year, they renegotiate the balance of the loan at a better rate of 7.5% compounded monthly and they increase the remaining term by 5 years. Determine the size of their monthly payments after renegotiation. This is another problem where we're going to have to break it down into smaller components and put it together at the end. First of all, we need to determine what the size of the monthly payment is with the original loan. We've borrowed $100,000 at 9% compounded monthly, and the term is 9 years. So we are going to start off with a term of 9 years. So your time diagram is going to start off with a 9-year term, and the payments are monthly, so that would be 9 times 12 months per year. That's a total of 108 monthly payments. So 0, 1, 2, 3, all the way up to 108 monthly payments of R dollars at the end of every month. So that would be R dollars at the end of every month for the 108 months. Now the question is, where does the $100,000 loan belong? And the answer is it belongs at the present value because we borrowed that money today, or the couple borrowed that money today. So that $100,000 represents the present value. That's where your focal date is going to be originally. Your focal date is going to be at the 0 point. So we're going to use the present value formula to solve for the monthly payment on the loan at 9% compounded monthly. Well, 9% compounded monthly amounts to 0.09 divided by 12, or 0.75% per month. So using the present value formula, we've got $100,000 is equal to the payment size per month multiplied by the present value factor, 1 minus 1.0075 per month. There's 108 payments, so that would be minus 108 divided by 0.0075 per month, and we're going to solve for the payment size. The annuity factor that's inside the factor here works out to be 173.839 and so on. So we've got payment is equal to $100,000 divided by 73.839. And again, I encourage you to use your memory key to store the entire value of the annuity factor to solve for the payment size. So the regular monthly payment on the loan is originally $13.54 So $13.54 per month. Now in the next phase of this problem, you realize that they renegotiate the balance of the loan at a better rate after 1 year. So what we need to do then is determine the balance or the outstanding balance of the loan after the 1-year period has gone by. So let's do that with the information that we have here. We now know that after 1 year has gone by, we have made 12 payments of $13.54. So we've made $13.54. 12 regular and equal payments of $13.54 on this $100,000 loan. So $13.54. I'm going to wrap an annuity bus around that so that I can emphasize here that I've got an annuity of 12 payments of $13.54. So N is equal to 12 payments. The original value of the loan was $100,000 when it was taken out. And I want to know what the balance is on that loan. So my focal date is going to be here, the balance after 1 year. So the balance at year 1 is going to be equal to the difference between what the loan would be worth on that focal date minus the value of the payments on that focal date. So you'll notice that the focal date is in the future. So the value of the loan would earn interest at 1 plus I to the power of n for a certain number of interest periods, and the future value of the annuity would be simply the future value of the payments. So let's see what we have here with this problem. We've got the balance at year 1 would be the value of the loan minus the value of the payments on that focal date. And so the value of the loan is going to be $100,000 with interest for 12 interest periods. So that would be we'd multiply that by 1.0075 exponent 12. Subtract from that $13.54 and 29 cents multiplied by the annuity factor, because the $13.54 is part of an annuity. So that would be 1.0075. We've got 12 payments in 1 year minus the 1 divided by 0.0075. So that gives us a value of $109,380 and 69 cents. Subtract 16,938 and 90 cents. The $109,000 represents the value of the loan if no payments were made. So $100,000 would have earned $9,000 in interest, or $93.80 in interest. But we did make some payments, and in fact we made 12 payments of $13.54. So the value of those payments must be subtracted from that loan balance. So in order to determine our balance now at year one, our balance at year one is going to be given with a difference of $92,441.79. So that would be the balance at year one. What do we do with that information now? This $92,000 now becomes the amount of money that they need to borrow at the lower rate. They're getting a better rate now. So they're going to borrow for an additional 5 more years. Now you see, they have paid 1 year of their original 9-year loan, so that means that they have 8 years left on the loan, plus they're going to add another 5 years to the amortization period, so that gives us a total of 13 years. So what that means is that when they borrow this $92,000, they're going to have a total of 8 plus 5. 8 plus 5 is going to be 13 years of monthly payments, and that 13 years of monthly payments is 13 times 12, or 156 monthly payments. So we've got 1, 2, 3, all the way up to 156 monthly payments of our dollars paid at the end of every month, with an opening balance, a new balance of $92,441. So the new balance will be equal to $92,441 and 79 cents, and that represents the present value of the new loan. So here's our annuity now, and what we need to do is to figure out what the payment size is going to be according to the new rate. The new lower interest rate is a nominal rate of 7.5% compounded monthly. So that means that the interest rate I is equal to 0.075 divided by 12, or 0.00625 per month. So that's the new rate that they're going to be using on the renegotiated loan. So now we've got $92,441.79 is equal to the payment size multiplied by the present value factor, because we're using the present value here. So it's going to be 1 minus 1.00625. Exponent is going to be negative 156 divided by 0.00625. So working out what this factor is, it'll end up being 99.4658 and so on. Make sure that you store that factor in your memory key. And because you're multiplying that by the payment size, in order to solve for the payment, you need to divide both sides by that factor. So we've got $92,000 divided by the factor of 99.465. It ends up being that the monthly payment works out to $929.38. So $929.38. So the monthly payment reduces to $929.38. But don't forget that they've actually added 5 years to their amortization period. They've gone originally from a 9-year loan to a to a 14 years that they're going to be making the payments over. So I don't think there's going to be very much of a savings here. Sometimes it doesn't pay to negotiate for a longer term and end up making smaller payments because you're making those payments for a longer time period. On this last page, we'd like to discuss with you use of the calculator functions for working out the solution to some of these problems with annuities. But I would like to emphasize again that irrespective of using the built-in functions on your calculator, you still will need to know whether you're working with the present value or future value. So it's very important that you set up a time diagram irrespective of using the functions. A family wants to borrow $60,000 for a home improvement project and can obtain financing at 8.5% compounded monthly for a 5-year term. So your time diagram is going to show that the $60,000 is at the present value. So the present value is $60,000. So on your calculator, you're going to key in PV or $60,000 and you're going to press the PV key. In addition to that, you're going to enter in the nominal interest rate of 8.5% compounded monthly. So the way you do that is you key in 8.5 and press the I/Y key. That's the interest rate compounded. Now we don't know what the compounding period is until we hit second function IY, and with second function IY you'll be entering in the PY and the CY values. PY is 12 payments per year. Hit the down arrow button to go to CY. CY is the compounding periods per year. It should also be 12 in this case because the payment periods and the interest periods coincide. Go second quit or press second function quit to get out of the IY function and enter in N as the number of payments. So you're going to key in 60 for N, and then you're going to press the compute function, CPT, for compute, and you're going to compute the payment size. And what you'll notice is that the payment size ends up being a negative number. One point that I'd like to make is that when the present value is positive, that means that you've got a positive value for the present value, the payments are going to be negative. They are the opposite sign. So the money in is the size of the loan. Money in is plus $60,000. Money out is what you're paying on that loan, $1,230.99. So always, if the payments are negative, the present value will be positive. If the future value is positive, the payments will be negative. So keep in mind that the present value or future value will be opposite in sign to the payments. It really doesn't matter which one you use as positive and which one is negative. They will always be the opposite in sign.